Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're someone who prefers drifting off to the quiet mysteries of the cosmos rather than tossing and turning in silence. Either way, you're in the right place. Tonight's journey is crafted just for you. You have nothing to do but rest. Let your mind soften, your breathing slow, and allow yourself to float gently into the story we're about to explore together. Because tonight, we're following the ancient wanderers of our solar system, comets. These luminous travelers, born in the frozen darkness beyond the planets, occasionally swing inward toward the sun, trailing brilliant tails of ice and dust across the night sky. For thousands of years, they've appeared without warning, sparking wonder, fear, and curiosity in equal measure. They've been called harbingers of doom, messengers from the gods, and more recently, time capsules from the birth of our solar system itself. We'll drift through their origins in the distant reaches of space, explore what they're made of, follow their long journeys through the darkness, and discover what happens when they venture close to the sun's warmth. You'll hear about famous comets that have graced our skies throughout history, from Halley's periodic return to the spectacular appearance of Hale-Bopp. We'll learn what spacecraft missions have revealed when they visited these icy bodies up close, and we'll consider what comets can tell us about where we came from and perhaps even where we're going. Some of what you hear might surprise you, spark a gentle curiosity, or simply provide a soft backdrop as you drift toward sleep. And just before we begin our journey, if these calm explorations into the cosmos help you unwind or give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps others discover this quiet corner of the universe, one sleepy soul at a time. Now, let's begin. The anatomy of a comet. To understand comets, we must first understand what they are at their core. When astronomers look at a comet through a telescope, or when a spacecraft ventures close enough to photograph one, they were seeing something remarkably simple in structure, yet profound in its implications. A comet, in its most basic form, is a small, irregular body composed primarily of ice and dust. These cosmic snowballs, as they're sometimes affectionately called, are typically just a few kilometers across, though some can stretch much larger. The heart of every comet is its nucleus. This solid core is where everything else originates. Picture a mountain of dirty ice floating through the emptiness of space, its surface blackened by radiation and cosmic dust. Its interior a mixture of frozen water, frozen carbon dioxide, frozen methane, and frozen ammonia, all bound together with rocky particles and complex organic molecules. The nucleus is ancient, largely unchanged, since it formed over 4.5 billion years ago in the outer reaches of our infant solar system. Most cometary nuclei are surprisingly dark. They reflect only about 3 to 4% of the sunlight that falls upon them, making them darker than coal, darker than asphalt. This darkness comes from the organic compounds that coat their surfaces, materials that have been altered by billions of years of exposure to cosmic radiation. When scientists first got close-up images of cometary nuclei from spacecraft missions, they discovered surfaces marked by pits, cliffs, smooth plains, and rough terrain. These aren't perfectly round objects. They're irregular, potato-shaped or even dumbbell-shaped bodies, tumbling slowly through space. The composition of a comet's nucleus is what makes these objects so scientifically precious. Water ice makes up a significant portion, perhaps 50 to 80% of the total mass. But it's not alone. Carbon dioxide ice is abundant, as are frozen methane and ammonia. Mixed throughout this icy matrix are dust particles, silicates similar to sand on Earth, carbonates, metal sulfides including pyrite, which we know as fool's gold, and incredibly complex organic molecules. These organics include polycyclic aromatic hydrocarbons, compounds found on Earth in coal and tar, as well as amino acids and other building blocks that could, under the right circumstances, contribute to the chemistry of life. But a comet is more than just its nucleus. When a comet's elongated orbit brings it close enough to the Sun, something remarkable happens. The Sun's heat begins to warm the frozen nucleus, and the ices within start to sublimate, transforming directly from solid to gas without passing through a liquid phase. This outgassing creates what we call the coma, a vast, glowing atmosphere that envelops the nucleus. The coma can be enormous, stretching hundreds of thousands of kilometers across, sometimes growing larger than the planet Jupiter, even though the solid nucleus hiding at its center might be only 10 or 20 kilometers wide. To put this in perspective, if the nucleus were the size of a marble, the coma surrounding it could be as wide as a football field or larger. This fuzzy, glowing envelope is what makes a comet visible from Earth, even when the nucleus itself would be far too small and dark to see. Within the coma, water molecules dominate. As they stream away from the nucleus, they're quickly broken apart by ultraviolet light from the Sun through a process called photodissociation. This destruction of water molecules produces hydrogen and oxygen, which contribute to the coma's glow. The coma also contains dust particles, ranging from microscopic grains to larger pebbles, all liberated from the nucleus as the ice holding them together sublimates away. Then come the tails, perhaps the most spectacular features of any bright comet. Most comets develop two distinct tails when they venture into the inner solar system, and these tails can stretch for millions upon millions of kilometers, making comets among the largest objects in the solar system, at least in terms of the space they occupy. The ion tail, also called the plasma tail or gas tail, is composed of electrically charged particles, ions and electrons that have been stripped from the neutral gases in the coma. This tail glows with a distinctive blue color, fluorescing in the solar wind. The solar wind, that constant stream of charged particles flowing outward from the Sun, pushes these ions directly away from the Sun with considerable force. As a result, the ion tail is typically straight, like an arrow pointing directly away from our star. It can be extremely long, sometimes stretching more than 100 million kilometers behind the comet. The dust tail is different. Composed of larger, heavier particles that were once embedded in the nucleus's ice, the dust tail curves gracefully, lagging slightly behind the comet's motion through space. These particles, ranging from microscopic specks to grains of sand, reflect sunlight, giving the dust tail a yellowish or white appearance. The curve of the dust tail comes from the fact that these heavier particles respond more slowly to the pressure of sunlight pushing them away from the Sun. As the comet moves along its orbit, it leaves these particles behind in its path, creating that characteristic sweeping, curved appearance that makes bright comets so photogenic. Remarkably, because both tails are pushed away from the sun by solar radiation and the solar wind, a comet's tails don't always stream behind it like the wake of a boat. When a comet is approaching the sun, heading inward through the solar system, its tails stream behind as you might expect. But when the comet rounds the sun and begins its journey back outward to the cold darkness from which it came, its tails sweep ahead of it, pointing away from the sun, even as the nucleus moves in the opposite direction. The comet, in effect, travels tail first on its outbound journey. Some comets also display what's called an anti-tail, a spike of light that appears to point toward the sun. This isn't actually a tail pointing in the wrong direction. Instead, it's an optical illusion created when Earth passes through the plane of the comet's orbit. And we're looking edge-on at the sheet of dust particles the comet has left behind. From our perspective, this dust sheet can briefly appear as a spike extending sunward, though it's still just dust being pushed away from the sun, seen from an unusual angle. The size and brightness of a comet's coma and tails depend on many factors. How active the nucleus is, how close the comet gets to the sun, how large the nucleus is, and how much volatile material it still contains. A comet making its first pass through the inner solar system, fresh from the frozen outer reaches, might put on a more spectacular show than one that has made many previous passes and lost much of its ice. Each time a comet visits the sun, it loses mass. Some of the most active comets can shed millions of kilograms of material per second when they're closest to the sun. The nucleus, the coma, the tails, all of these components together create the phenomenon we recognize as a comet. But these structures are temporary. Far out beyond Mars, far from the sun's warmth, a comet is just its nucleus, a dark, frozen rock tumbling silently through the void, giving no hint of the spectacular transformation it will undergo if and when it falls toward the sun once more. The comet in the darkness and the comet with its glorious tails are the same object, just seen at different points in its long, elliptical journey through our solar system. Origins and reservoirs. To understand where comets come from, we need to travel to the far reaches of our solar system, to places so distant that the sun appears as just another bright star in the sky, places where temperatures hover just a few degrees above absolute zero, where ice is as solid as steel, and darkness is the natural state of existence. Comets are born in two primary regions, each vastly different in character, yet both serving as enormous storage reservoirs, cosmic deep freezers preserving billions upon billions of these icy bodies. The first and closer of these regions is the Kuiper belt, a disc-shaped zone that begins beyond Neptune's orbit, roughly 30 astronomical units from the Sun. An astronomical unit, or AU, is the distance from Earth to the Sun, about 93 million miles, or 150 million kilometers. The Kuiper belt extends outward from this starting point to perhaps 50 AU or more, creating a vast donut of space populated by countless small icy bodies. In the Kuiper belt, temperatures are cold enough that volatile materials like water, methane, carbon dioxide, and ammonia remain frozen solid. Here, small bodies orbit the Sun in the same general plane as the planets, in relatively circular paths that keep them at these enormous distances. These objects, sometimes called Kuiper Belt objects or KBOs, range in size from tiny ice balls just meters across to dwarf planets like Pluto and Eris, which are thousands of kilometers in diameter. The Kuiper Belt is thought to be the source of most short-period comets. The comets that orbit the Sun with periods of less than 200 years. These comets, when we see them, are typically approaching from near the plane of the solar system, the same general region where the planets orbit. They don't come from random directions but follow somewhat predictable paths because they originated in this flattened disk beyond Neptune. Jupiter family comets, which orbit with periods of less than about 20 years, are particularly associated with the Kuiper Belt. They get their name because Jupiter's enormous gravity plays a significant role in shaping their orbits. How does a Kuiper Belt object become a comet? The answer lies in gravitational perturbations. Neptune, massive and powerful, occasionally nudges objects in the Kuiper Belt through gravitational interaction. Sometimes a close encounter with Neptune or another gravitational influence can change a KBO's orbit, sending it on a path that brings it closer to the Sun. Once an object's orbit takes it into the inner solar system, into the realm where the Sun's heat can cause ice to sublimate, it becomes what we recognize as an active comet, complete with coma and tails. But the Kuiper Belt, vast as it is just the beginning. Far beyond it lies a structure so enormous, so distant, that it took astronomers decades to even theorize its existence. This is the Oort cloud, named after Dutch astronomer John Oort, who first proposed its existence in 1950. While the Kuiper Belt is a disk, the Oort cloud is a sphere, a vast shell of cometary bodies completely surrounding our solar system in all directions. The Oort cloud is thought to begin somewhere around 2,000 astronomical units from the Sun, well beyond the Kuiper Belt, and extend outward to perhaps 100,000 AU, possibly even farther. To put this distance in perspective, the Oort cloud reaches nearly halfway to the nearest star. Light from the Sun takes more than a year to reach the outer edges of the Oort cloud. Out there, in that immense darkness, temperatures are only a few degrees above absolute zero, and objects orbit the Sun so slowly that a single orbit might take millions of years to complete. The Oort cloud is thought to contain trillions of icy bodies, perhaps even a trillion individual comets, though most are very small. The total mass of all these objects combined is estimated to be roughly equivalent to a few Earth masses, maybe as much as 100 Earth masses, though the uncertainty is large. These objects are spread across such an enormous volume of space that the average distance between neighboring comets is measured in billions of kilometers. It's not a dense cloud. If you were standing on one Oort cloud comet, you likely wouldn't be able to see any others with the naked eye. They'd be too far away, too small, and reflect too little light. The Oort cloud is the source of long-period comets, those majestic visitors that appear without warning, sweep through the inner solar system on elongated orbits, and then disappear back into the darkness, not to return for thousands, tens of thousands, or even millions of years. These comets can approach from any direction, from above the plane of the solar system or below it, from the north or the south, because the Oort cloud is spherical. Their orbits can be tilted at any angle, including retrograde orbits that carry them around the Sun in the opposite direction from the planet's motion. What sends an Oort cloud comet on its long plunge toward the Sun? The answer is disturbance. At those enormous distances, the Sun's gravity, while still present, is very weak. Other forces become significant. A passing star, even if it's light years away, can exert just enough gravitational influence to nudge an Oort cloud comet, changing its orbit slightly. Similarly, the gravitational tide from the Milky Way galaxy itself, the combined pull of all the stars in the galaxy, can affect these distant objects. Sometimes these perturbations are just enough to send a comet falling inward on an elongated ellipse toward the Sun. How did these vast reservoirs of comets form in the first place? The answer takes us back to the birth of the solar system itself, over 4.5 billion years ago. Our solar system formed from a vast cloud of gas and dust, a nebula that began to collapse under its own gravity. As this material fell inward, it began to spin, flattening into a disk. At the center, material accumulated and heated until nuclear fusion ignited, creating the Sun. In the disk around the young Sun, dust grains collided and stuck together, gradually building up larger and larger bodies. Close to the Sun, where temperatures were high, only materials with high melting points could remain solid. This is where the rocky planets formed: Mercury, Venus, Earth, and Mars. But farther out, beyond what astronomers call the frost line, temperatures were cold enough for water and other volatile compounds to freeze. This is where the giant planets formed, and it's also where comets began to accumulate. In the region that would become the Kuiper belt and the scattered disk beyond it, small icy bodies formed from the condensation of water, methane, ammonia, and carbon dioxide, mixed with dust and rock. These were the building blocks of the outer solar system. Some of these icy bodies accumulated into larger objects, eventually forming planets like Uranus and Neptune. But countless smaller bodies remained, preserved in the cold, unable to accumulate into anything larger. The Oort cloud's origin story is slightly different. Many astronomers believe that the objects now in the Oort cloud actually formed closer to the Sun, perhaps in the region where Uranus and Neptune orbit today. As the giant planets grew and migrated, changing their orbital distances, they gravitationally scattered countless smaller icy bodies. Some were thrown inward, possibly delivering water and organic materials to the inner solar system. Others were flung outward with such force that they reached the distant fringes of the Sun's gravitational influence, where they settled into the vast, spherical cloud we call the Oort cloud. This scattering process was not clean or efficient. Most objects flung outward by the giant planets escaped the solar system entirely, lost to interstellar space. But a small fraction, perhaps just 4% of the ejected objects, had their orbits captured into the Oort cloud. Over hundreds of millions of years, as the solar system settled into its current configuration, The Oort cloud was populated with these refugees from the inner system, comets that had formed closer to the Sun, but were now banished to the cold outer darkness, waiting for the rare gravitational nudge that would send them falling back toward the warmth they left behind billions of years ago. Some researchers have proposed an additional source for Oort cloud comets. If the Sun formed in a stellar nursery, a cluster of stars as most stars do, then in the solar system's early days, other stars would have been much closer than they are now. In those crowded conditions, gravitational interactions between neighboring stellar systems might have allowed the young Sun to capture some comets from its stellar siblings, or conversely, to lose some of its own comets to other stars. The Oort cloud, then, might contain not only our solar system's native comets, but also immigrants from other planetary systems, visitors from stellar neighbors the Sun hasn't seen in over 4 billion years. Both the Kuiper belt and the Oort cloud are essentially invisible to us. We can observe some of the larger objects in the Kuiper belt with powerful telescopes, and we've even sent the New Horizons spacecraft to fly past Pluto and other KBOs. But the Oort cloud has never been directly observed. It's too distant, and its constituent comets are too small and dark to see at such extreme ranges. We know it exists only because of the comets it sends our way, objects that emerge from the darkness, light up as they approach the Sun, and reveal through their orbital characteristics that they must have come from an enormous spherical reservoir surrounding the solar system. These distant regions, the Kuiper belt and the Oort cloud, are more than just parking lots for comets. They're archives, repositories of primordial material that has remained largely unchanged since the solar system's formation. The comets stored there preserve a chemical and physical record of conditions in the early solar nebula, before planets had fully formed, before the Sun had burned away the remaining gas and dust. When a comet from the Oort cloud visits the inner solar system, it's bringing us a sample of that ancient material, a time capsule from the dawn of our cosmic neighborhood. Orbital mechanics and types. The orbits of comets are among the most diverse and extreme in the solar system. While planets travel around the Sun in nearly circular paths, staying roughly in the same plane, comets follow wildly elongated ellipses, parabolas, or even hyperbolas, and they can approach the Sun from any direction. Understanding these orbits helps us classify comets and trace them back to their origins in the Kuiper belt or Oort cloud. Astronomers classify comets primarily by their orbital periods, the time it takes them to complete one orbit around the Sun. This classification reveals where a comet likely originated and how it came to be in the orbit we observe. The first major category is short-period comets, defined as those with orbital periods of less than 200 years. These comets have been captured into relatively stable orbits, though stable is a relative term in the dynamic environment of the solar system. Many short-period comets have been observed multiple times as they return again and again to the inner solar system. Short-period comets are further divided into two groups. Jupiter family comets have orbital periods typically less than 20 years. They orbit in the same plane as the planets, with relatively modest inclinations to the ecliptic, usually less than 35 degrees. These comets are thought to originate in the Kuiper belt, or the scattered disk, and they owe their current orbits to gravitational encounters with Jupiter. This massive planet, with its enormous gravitational field, can capture comets passing nearby, altering their trajectories and shortening their orbital periods. Jupiter acts like a gravitational shepherd, collecting comets into its family. Halley-type comets represent the second group of short-period comets. These have orbital periods between 20 and 200 years, and they often have much higher inclinations than Jupiter family comets. Some even travel in retrograde orbits, moving around the Sun in the opposite direction from the planets. These comets may have originated in the Oort cloud, but were gravitationally perturbed by one of the giant planets on a previous pass. Their orbits shortened from the millions of years typical of long-period comets down to the century-scale periods we observe today. Long-period comets are the second major category, and they're the spectacular visitors that can appear without warning and then vanish for thousands or millions of years. These comets have orbital periods greater than 200 years, with some taking hundreds of thousands or even millions of years to complete a single orbit. Many long-period comets appear to be on nearly parabolic orbits, meaning they're moving just slightly slower than the escape velocity needed to leave the solar system entirely. These comets are thought to come from the Oort cloud, nudged inward by gravitational perturbations from passing stars or the galactic tide. The inclinations of long-period comets are essentially random. They can approach from any direction, from high above the plane of the solar system or from far below it, at any angle in between. This isotropic distribution is a key piece of evidence supporting the spherical Oort cloud hypothesis. If long-period comets came from a flattened disk like the Kuiper belt, we'd expect to see them clustered near the plane of the solar system, but we don't. They come from all directions, consistent with the spherical source. There's also a third, rarer category, hyperbolic comets. These objects are moving faster than escape velocity. They're on open orbits that will carry them past the Sun just once before they leave the solar system forever, headed out into interstellar space. For many years, astronomers debated whether true interstellar comets that originated in other stellar systems, could visit our solar system. The question was answered definitively in 2017 when the first confirmed interstellar object, Oumuamua, passed through the inner solar system. Though Oumuamua showed no obvious cometary activity, its hyperbolic orbit proved it came from beyond our solar system. In 2019, a second interstellar object, Comet Borisov, was discovered, and this one clearly displayed cometary activity with a visible coma and tail. Interstellar comets may pass through our neighborhood more often than we realized, though most are probably too faint to detect. To better understand and classify cometary orbits, astronomers use a mathematical quantity called the Tisserand parameter, developed by French astronomer Félix Tisserand in the 19th century. This parameter takes into account a comet's orbital characteristics relative to Jupiter's orbit, and remains approximately constant even when the comet's orbit is perturbed by Jupiter. The Tisserand parameter helps astronomers identify whether a comet observed in one apparition is the same object as a comet observed years or decades earlier, even if Jupiter's gravity has significantly altered its orbit between appearances. Jupiter-family comets typically have Tisserand parameters between 2 and 3. Halley-type and long-period comets have values less than 2. Asteroids, which follow different types of orbits, generally have Tisserand parameters greater than 3. This mathematical tool has proven invaluable for tracking comets and understanding how their orbits evolve over time. The orbits of comets are not fixed. They change, sometimes dramatically, due to gravitational perturbations from the planets, especially Jupiter and Saturn. A comet passing close to one of these giant planets can have its orbit completely transformed. A long-period comet from the Oort cloud might be captured into a short-period orbit by Jupiter, joining the Jupiter family. Conversely, a comet might receive a gravitational kick that sends it out of the solar system entirely on a hyperbolic escape trajectory, or it might be thrown onto a sun-grazing orbit that brings it so close to the sun that it's destroyed by tidal forces and heat. Comets themselves can also change their own orbits slightly through a process called outgassing. As ice sublimates from the nucleus, the escaping gas carries momentum. If the nucleus is rotating, and outgassing is stronger on one side than the other, the rocket-like thrust from escaping gas can very slowly alter the comet's trajectory. This effect is usually small, but over many orbits it can accumulate, causing a comet to arrive slightly earlier or later than predicted by gravitational calculations alone. The eccentricity of a comet's orbit describes how elongated its path is. An eccentricity of 0 represents a perfect circle. An eccentricity approaching 1 represents an extremely elongated ellipse, with the comet spending most of its time far from the Sun and only briefly plunging through the inner solar system. An eccentricity of exactly 1 represents a parabola, the boundary between bound and unbound orbits. An eccentricity greater than 1 represents a hyperbola, an open orbit that will carry the object away forever. Most comets that we observe have eccentricities very close to 1, reflecting the fact that they're on extremely elongated ellipses that stretch out to the Oort cloud or beyond. Perihelion, the point in a comet's orbit where it comes closest to the Sun, is a crucial characteristic. Some comets have perihelia inside Mercury's orbit, bringing them closer to the Sun than any planet. These comets experience intense solar heating, which can cause spectacular outbursts of gas and dust, but can also lead to the comet's destruction. Sun-grazing comets, a special category that includes the Kreutz family of sun-grazers, have perihelia that bring them within a few solar radii of the Sun's surface. Many sun-grazers don't survive their close approach. They're torn apart by tidal forces or completely vaporized by the intense heat. Aphelion, the farthest point in a comet's orbit, tells us how far out the comet travels when it's at its most distant from the Sun. For short-period comets, aphelion might be near Jupiter's orbit, around 5 AU, or out near Neptune at 30 AU. For long-period comets, aphelion can be tens of thousands of AU away, well into the Oort cloud. These comets spend the vast majority of their orbital period at aphelion, moving slowly through the frozen darkness, with only a tiny fraction of their orbit carrying them through the inner solar system where we can see them. Understanding cometary orbits isn't just an academic exercise. It has practical applications. If we can precisely determine a comet's orbit, we can predict when and where it will appear in the future, allowing astronomers to plan observations. We can also trace the comet's orbit backward into the past, determining when it might have visited the inner solar system previously, and searching historical records for possible earlier observations of the same object. More importantly, understanding cometary orbits helps us assess whether any particular comet might pose a threat to Earth. While the probability of a large comet impact in any given year is extremely low, such an event would be catastrophic. By tracking comets and calculating their orbits with precision, astronomers can determine whether any will pass dangerously close to Earth, and with sufficient warning, we might be able to take action to deflect a threatening object, the journey inward. Imagine a comet in the darkness beyond Neptune, a frozen chunk of ice and rock perhaps 5 kilometers across, tumbling slowly through the void. At this distance, roughly 30 to 50 astronomical units from the Sun, temperatures hover around 40 to 50 Kelvin, negative 230 to negative 220 Celsius. The comet's surface is frozen solid, harder than concrete. It has no atmosphere, no activity, nothing to distinguish it from the countless other small bodies drifting in the Kuiper belt. It's been this way for millions of years, perhaps since the solar system formed over 4.5 billion years ago. Then something changes. Perhaps a gravitational interaction with Neptune has altered its orbit slightly, or maybe the cumulative effect of many small perturbations over millennia has finally shifted its trajectory. The comet begins to fall inward, toward the Sun. The change is imperceptible at first. The comet's velocity increases only slightly, and its appearance remains unchanged. Months pass, then years, then decades. Slowly, gradually, the comet draws closer to the inner solar system. As it crosses the orbit of Neptune, then Uranus, still nothing visible happens. The comet remains dark and frozen. But as it approaches Saturn's orbit, about 9 or 10 astronomical units from the Sun, something begins. The Sun's radiation, though still weak at this distance, is strong enough to start warming the comet's surface. Deep within the porous ice of the nucleus, sublimation begins. Frozen carbon dioxide, which sublimates at lower temperatures than water ice, starts to transition directly from solid to gas. Tiny amounts of vapor seep through cracks and pores in the surface, carrying microscopic dust particles with them. At first, this activity is extremely subtle, detectable only with powerful telescopes and sensitive instruments. The comet might brighten very slightly, but it still appears star-like, just a point of light moving slowly against the background of distant stars. But this is the beginning. Once started, the process of sublimation accelerates as the comet continues inward. By the time the comet reaches Jupiter's orbit at about 5 astronomical units, the sublimation has increased significantly. Water ice on the surface and in the subsurface begins to sublime. The rate of outgassing increases. Now, when astronomers point their telescopes at the comet, they see something more than just a point of light. The comet has developed a coma, a faint, fuzzy envelope surrounding the nucleus. This marks the transition from an inert Kuiper belt object to an active comet. The coma grows as the comet approaches. Gas and dust stream away from the nucleus at speeds of hundreds of meters per second, expanding outward into space. Water molecules, carbon dioxide, carbon monoxide, methane, ammonia, and dozens of other compounds flow out from the sublimating ice. Dust particles, ranging from sub-micron-sized grains to pebbles, are entrained in this gas flow and carried away from the nucleus. The coma expands to hundreds, then thousands, then tens of thousands of kilometers in diameter. Around 3 to 4 astronomical units from the Sun, roughly in the asteroid belt region between Mars and Jupiter, the comet begins to develop tails. The solar wind, that stream of charged particles constantly flowing outward from the Sun, starts to have a noticeable effect on the gas in the coma. Ultraviolet light from the Sun ionizes some of the gas molecules, stripping away electrons and creating ions. These ions are caught in the solar wind and swept directly away from the Sun, forming the beginnings of an ion tail. Simultaneously, light pressure from the Sun's photons begins pushing on the dust particles in the coma. Unlike the solar wind, which affects only charged particles, light pressure affects anything that reflects or absorbs light. The dust particles, though electrically neutral, feel this pressure and are slowly accelerated away from the Sun. Being heavier than individual ions, they respond more slowly, creating the curved dust tail. As the comet continues inward, passing the orbit of Mars and approaching Earth's orbit at 1 AU, the activity intensifies. The production rate of gas and dust increases dramatically. The comet is now releasing thousands, tens of thousands, perhaps millions of kilograms of material every second. The coma swells to enormous proportions, sometimes growing larger than Jupiter. The tails stretch behind the nucleus for millions of kilometers, sometimes reaching lengths of 1 astronomical unit or more, making the comet one of the largest structures in the solar system by volume, though almost all of that volume is empty space with just a whisper of gas and dust. The ion tail, glowing blue from the fluorescence of ionized carbon monoxide, stretches in a nearly straight line directly away from the Sun. It can change rapidly, sometimes developing kinks or disconnection events where part of the tail breaks away from the comet entirely, swept downstream by disturbances in the solar wind. The dust tail, glowing yellow or white as it reflects sunlight, curves gently behind the comet, broader and more diffuse than the ion tail. For bright comets on favorable orbits, this is when they become spectacular naked-eye objects, visible even from light-polluted cities. This is when newspapers write articles, when people who never look at the night sky suddenly venture outside at dusk or dawn to catch a glimpse of the visitor from the outer solar system. This is when a comet captures the public imagination. Finally, the comet reaches perihelion, its closest approach to the Sun. For a comet with a perihelion inside Earth's orbit, perhaps at 0.5 AU or even closer, this is the moment of maximum activity. The Sun's heat at this distance is intense. Surface temperatures on the sunlit side of the nucleus can climb above the freezing point of water. Ice sublimates rapidly, gas production peaks, and the comet shines at its brightest. Jets of gas erupt from active areas on the nucleus's surface, visible in spacecraft images as bright plumes streaming into space. The coma and tails reach their maximum extent. But perihelion is brief. Within days or weeks, the comet begins to recede from the Sun, heading back out toward the cold, outer solar system. As it does, an interesting thing happens. Because the tails are pushed away from the Sun by the solar wind and light pressure, and not by the comet's motion through space, the tails now precede the nucleus. The comet travels tail first on its outbound journey, with the ion tail pointing ahead and the nucleus following behind. As the comet moves outward past Earth's orbit, past Mars, back toward Jupiter, the activity begins to decline. The Sun's radiation weakens with distance. Surface temperatures on the nucleus drop. Sublimation rates decrease. The gas production slows, the coma shrinks, the tails fade and eventually disappear entirely. By the time the comet crosses Jupiter's orbit heading outward, it has returned to dormancy. The spectacular display is over. The comet is once again just a dark, frozen nucleus, its surface refrozen. Its activity ceased, heading back out to the distant reaches of its orbit. In the Kuiper belt or the Oort cloud, depending on its orbital period, the comet will spend the vast majority of its orbital period. If it's a long-period comet with a period of thousands of years, it might not return to the inner solar system for 100 generations of human lifetimes. If it's a short-period comet like Halley's, it will return in a matter of decades. But for now, its moment in the Sun is over. It drifts outward into the darkness, inactive and invisible, a small frozen world carrying traces of the solar system's most ancient past, waiting for its next chance to light up the skies of Earth. Halley's Comet, a historical journey. There is perhaps no single comet more famous, more studied, or more deeply woven into human history than Halley's Comet. For over 2,000 years, this cosmic wanderer has returned to the inner solar system every 75 to 79 years, appearing in Earth's skies like clockwork. Though for most of human history, no one realized that the brilliant comet that appeared in one generation was the same object that had appeared in their grandparents' or great-grandparents' time. Ancient records of Halley's Comet stretch back remarkably far. Chinese astronomers, who maintained meticulous records of celestial phenomena for millennia, documented what we now know to have been Halley's Comet as early as 240 BC, and possibly earlier. These ancient observers saw the comet not as a natural phenomenon to be studied, but as a portent, a sign from the heavens that foretold disaster, the death of kings, war, or upheaval. Under the Chinese theory of Wu Qing, the 5 elements, comets represented an imbalance of yin and yang, a disruption in the cosmic order that required attention from the emperor and his advisors. The appearance of Halley's Comet was taken so seriously that it influenced imperial decisions. In 684 CE, Emperor Ruizong of Tang abdicated his throne following a comet apparition, interpreting the celestial visitor as a sign that his reign was out of favor with heaven. Comets were thought to have military significance. The breakup of a comet in 35 CE was interpreted as portending the destruction of one warring faction by another, and indeed, the predicted defeat occurred. In Western history, one of the most famous early appearances of Halley's Comet occurred in 1066. As William, Duke of Normandy, prepared to invade England, the comet blazed in the spring sky. The Anglo-Saxons saw it as an omen of disaster for their King Harold. The Normans may have seen it as a sign of divine favor for William. That same year, William's forces defeated Harold at the Battle of Hastings, fundamentally changing English history. The comet's appearance was immortalized in the Bayeux Tapestry, a medieval embroidered cloth nearly 70 meters long that chronicles the invasion. In one panel, frightened observers point at the comet in the sky above them, while King Harold sits troubled on his throne. Latin text reads, "They marvel at the star." For centuries, comets remained mysterious and terrifying. Aristotle, the ancient Greek philosopher whose views dominated Western thought for over 1,000 years, had argued that comets were atmospheric phenomena, disturbances in the air below the moon. This view persisted until 1577, when Danish astronomer Tycho Brahe used careful parallax measurements to prove that comets must lie far beyond the moon, traveling through the space where the planets orbit. This was a revolutionary finding, demonstrating that the heavens were not immutable and perfect, but could be visited by transient objects. Even after Brahe's discovery, the nature of comets remained unclear. Did they orbit the sun, or did they travel through space in straight lines, never to return? In the 1680s, a bright comet appeared that would help answer this question. The young Edmund Halley, who would later become England's Astronomer Royal, observed this comet carefully. Around the same time, Halley was working closely with Isaac Newton, helping him develop and publish his laws of motion and gravitation in the monumental Principia Mathematica. Newton's laws provided the mathematical tools to analyze cometary motion, and Halley seized upon them. He collected historical observations of comets and calculated their orbits, looking for patterns. In 1705, Halley published his Synopsis of the Astronomy of Comets, in which he made a bold claim. He had found that 3 bright comets observed in 1531, 1607, and 1682 had remarkably similar orbital characteristics. Accounting for the gravitational influence of Jupiter and Saturn, Halley concluded that these were not 3 different comets, but 3 appearances of the same comet, returning approximately every 76 years. If he was correct, Halley predicted, the comet would return again in 1758. Halley would not live to see his prediction confirmed. He died in 1742 at the age of 85. But as 1758 approached, astronomers across Europe watched the skies eagerly. A team of French mathematicians, Alexis Clairaut, Joseph Lalande, and Nicole Reine-Lepaute, refined Halley's calculations, accounting more precisely for the gravitational effects of the outer planets. They predicted the comet would reach perihelion, its closest point to the Sun, in April 1759, give or take a month. On Christmas night, 1758, a German farmer and amateur astronomer named Johann Georg Palitzsch spotted a faint smudge of light in the constellation Pisces. It was the comet, returning just as Halley had predicted. As months passed, it brightened and developed a tail, becoming visible to observers across Europe and the Americas. The prediction was triumphantly confirmed. For the first time in history, a comet's return had been successfully predicted using mathematical laws. This was a profound moment for science, validating Newton's theory of gravitation and proving that comets were natural objects obeying physical laws, not omens or divine messengers. The comet was named Halley's Comet in honor of the man who first recognized its periodic nature. Since then, Halley's Comet has returned twice to the inner solar system, and astronomers have traced historical records backward, identifying dozens of earlier appearances. The comet has been observed during every passage for over 2,000 years, making it the most consistently documented comet in history. The comet's appearance in 1910 caused something of a sensation. Astronomers had learned that cometary tails contain various gases, and some worried that Earth would pass through Halley's tail. When spectroscopy revealed cyanogen, a mildly toxic gas, in the comet's tail, some newspapers published sensational stories about possible danger. Unscrupulous individuals sold comet pills that supposedly offered protection. In reality, cometary tails are so diffuse that passing through one has no noticeable effect on Earth. When Earth did pass through Halley's tail on May 19, 1910, nothing happened. The sky didn't turn strange colors. No one fell ill. Life continued normally. But the incident illustrated the powerful hold comets still had on the public imagination. The most recent apparition of Halley's Comet was in 1986, and this time humanity was prepared not just to observe from Earth, but to send spacecraft to meet the comet in space. It was an unprecedented international effort. Japan launched 2 spacecraft, Suisei and Sakigake. The Soviet Union redirected 2 spacecraft, Vega 1 and Vega 2, that had already successfully visited Venus, sending them on to encounter Halley. The United States contributed the ISEE-3 IACE spacecraft, though from a much greater distance. The European Space Agency launched Giotto, named after the Renaissance painter who had depicted Halley's Comet in a fresco. Giotto was the star of the mission. On March 13, 1986, this brave spacecraft plunged through Halley's coma at a relative velocity of over 68 kilometers per second, passing just 600 kilometers from the nucleus. For the first time, humanity saw what a cometary nucleus really looked like. Giotto's camera revealed an irregularly shaped, dark object measuring roughly 15 kilometers long and 8 kilometers wide. The nucleus was darker than coal, reflecting only 4% of the light that struck it. Jets of gas and dust erupted from specific active areas on the sunlit side, creating bright plumes that streamed into space. The rest of the surface appeared largely inactive, covered with a dark crust of organic material baked by billions of years of radiation exposure. These images revolutionized cometary science. Before Giotto, astronomers had models and theories, but now they had direct observations. Comets were indeed dirty snowballs, as astronomer Fred Whipple had proposed in 1950, but they were darker, more complex, and more variegated than expected. The 1986 apparition of Halley's Comet was not particularly favorable for viewing from Earth. The comet reached perihelion in February, at a time when it was on the opposite side of the Sun from Earth, creating some of the worst viewing conditions in recorded history. Add to this the increasing problem of light pollution from urbanization, and many people who tried to see the comet were disappointed. It never became a spectacular naked-eye object like it had in 1910 or during some earlier apparitions. But for astronomers, the wealth of spacecraft data more than compensated for the poor viewing from Earth. Halley's Comet is currently heading back out toward the outer solar system. It won't return to perihelion until mid-2061. Those of us alive today who remember the 1986 apparition, if fortunate, might live to see it return. For younger generations, the 2061 apparition will be their first opportunity to witness this famous comet, continuing a tradition of observation that stretches back over 2 millennia. Halley's orbit takes it out beyond Neptune's orbit to an aphelion of about 35 astronomical units. It's not a Jupiter family comet. Its orbit is highly inclined to the plane of the solar system, tilted about 18 degrees, and it travels in a retrograde direction, opposite to the planet's motion. This makes Halley a Halley-type comet, naturally, the prototype of that classification. Its orbital period varies slightly from apparition to apparition due to gravitational perturbations from the planets, ranging from as short as 74 years to as long as 79 years, with an average of about 76 years. Scientists calculate that the average short-period comet can complete perhaps 1,000 trips around the Sun before it exhausts its volatile ices and becomes inactive. Halley has been in its present orbit for at least 16,000 years, and possibly much longer. Based on calculations of how much mass it loses during each perihelion passage, the comet should be able to survive for tens of thousands of years more before it becomes a spent, inert object more like an asteroid than a comet. Halley's Comet is more than just a scientific object. It's a thread connecting generations, a cosmic clock marking time in human terms. Each appearance is separated by roughly a human lifetime, long enough that most people see it only once, if at all. It carries history with it, having been witnessed by the Babylonians, the Chinese, the Greeks, the Romans, medieval kings, Renaissance artists, and now by us with our spacecraft and telescopes and photographs. When it returns in 2061, it will be seen by a new generation, carrying its ancient ice and dust past Earth once more, a wanderer from the dawn of the solar system, still performing its slow dance around the Sun. Great comets through history. Throughout history, certain comets have captured humanity's attention more than others, burning themselves into collective memory not just through their scientific significance but through their sheer visual splendor. These are the great comets, brilliant enough to be seen easily with the naked eye, impressive enough to be remembered for generations, spectacular enough to inspire art, literature, and, in some cases, irrational fear. What makes a comet great is somewhat subjective, but generally, great comets combine several characteristics. They must be bright, typically reaching magnitude 0 or brighter, making them visible even from light-polluted areas. They often have impressive tails stretching across a significant portion of the sky. They're visible for an extended period, sometimes weeks or months, and crucially, they appear at a time when they can be seen by large populations of people, not hidden in the glare of the sun or visible only from unpopulated regions. In the late 20th century, one comet stands above all others in terms of public impact and viewing opportunity. This was Comet Hale-Bopp, officially designated 99501, which graced Earth's skies in 1997 and became probably the most widely observed comet in human history. Hale-Bopp's discovery story is a testament to the power of amateur astronomy. On July 23, 1995, Alan Hale, an astronomer in New Mexico, and Thomas Bopp, an amateur observer in Arizona, independently discovered the comet within hours of each other. Hale had been systematically observing known comets when he noticed an unfamiliar fuzzy object near the globular cluster M70 in the constellation Sagittarius. After confirming the object was moving against the background stars and checking that no known comet should be in that position, he reported his discovery. Bopp made his discovery under different circumstances. He didn't own a telescope, but was looking through a friend's instrument at a star party, observing deep sky objects, when he noticed the same mysterious comet. Both men submitted their observations to the Central Bureau for Astronomical Telegrams, the clearinghouse for astronomical discoveries, and both were credited as co-discoverers. What made the discovery immediately remarkable was the comet's brightness and distance. Hale-Bopp was discovered at a distance of about 7 astronomical units from the Sun, beyond Jupiter's orbit, yet it was already bright enough to be visible in amateur telescopes, shining at about magnitude 10.5. This suggested either a very active comet or one with an unusually wide nucleus. As observations continued, astronomers realized it was both. Hale-Bopp's nucleus was estimated to be about 40 kilometers in diameter, making it one of the largest cometary nuclei ever observed. For comparison, most comets have nuclei just a few kilometers across. Predicting how bright a comet will become is notoriously difficult. Comets are essentially unpredictable, capable of sudden outbursts or unexpected fade-outs. But as Hale-Bopp approached the inner solar system, it exceeded even optimistic predictions. By early 1997, as it approached perihelion, the comet had become spectacular, developing dual tails that were easily visible to the naked eye. Hale-Bopp reached perihelion on April 1, 1997, passing about 0.91 astronomical units from the Sun, inside Earth's orbit but not dramatically close. At its peak, the comet reached about magnitude -1, rivaling the brightest stars in the night sky. Its dual tails, one composed of ionized gas glowing blue and the other composed of dust reflecting sunlight in yellow and white, stretched across the sky. The gas tail extended straight back from the comet's head while the curved dust tail spread in a graceful arc. From dark sky locations, the tails could be traced for 20 degrees or more across the sky, a span equal to 40 times the apparent diameter of the full moon. What set Hale-Bopp apart from other comets was its visibility period. The comet was visible to the naked eye for a record-setting 18 months, from May 96 through November 987. This was twice as long as the previous record holder, the Great Comet of 1811. During the peak viewing months of March and April 97, the comet dominated the evening sky, visible even from light-polluted cities. By some estimates, 69% of Americans saw Hale-Bopp by April 9, 1997. Internationally, hundreds of millions of people viewed the comet, making it truly a global spectacle. For astronomers, Hale-Bopp was a bonanza. Because it was so bright and remained visible for so long, researchers could study it in unprecedented detail using instruments across the electromagnetic spectrum. They discovered that the comet's dust production rate was extremely high, reaching 2 million kilograms per second at peak activity. They detected numerous molecules in the coma, including water, carbon monoxide, carbon dioxide, methane, ammonia, formaldehyde, methanol, and many others. They even detected deuterium, a heavy form of hydrogen, which provided clues about the conditions under which the comet formed billions of years ago in the outer solar nebula. But Hale-Bopp's appearance also had a tragic footnote. In March 97, 39 members of the Heaven's Gate cult based in San Diego, California, committed mass suicide. The cult members believed that a spacecraft was following Hale-Bopp, and that by ending their earthly lives, they would be able to board this spacecraft and travel to a higher plane of existence. This belief was based on a misinterpretation of an image that appeared to show an object near the comet, though the object was later identified as a background star distorted by image processing. The tragedy served as a grim reminder that even in the modern age, with all our scientific understanding, comets can still grip the human imagination in irrational and dangerous ways. Hale-Bopp will return to the inner solar system in approximately 2,530 years, around the year 4380. Its orbital period was shortened by gravitational interactions with Jupiter during its 97 passage. When it last visited the inner solar system, around 2215 BC, the Egyptian pyramids were still relatively new, and cuneiform writing was the cutting edge of communication technology. No records of that apparition survive, though ancient civilizations certainly could not have missed such a bright comet. Before Hale-Bopp, another exceptional comet had appeared in the 1990s. This was Comet Hyakutake, officially C1996 B2, discovered by Japanese amateur astronomer Yuji Hyakutake in January 96. Though not as intrinsically bright as Hale-Bopp, Hyakutake passed very close to Earth, just 0.1 astronomical units or about 15 million kilometers, on March 25, 1996. This close approach made the comet appear spectacular. Its tail stretched across more than half the sky at its peak, creating a sight not seen in decades. Observers in dark locations reported the comet was bright enough to cast faint shadows. Hyakutake was visible for several months before Hale-Bopp took over as the comet of the decade. In 2010, Comet McNaught, SI 2006 P1, became the brightest comet in over 40 years, reaching magnitude -5.5 at its peak, brighter than Venus. Unfortunately, McNaught was best visible from the southern hemisphere, and even there, it was close to the sun in the sky, making observation challenging. But for those who saw it, Especially from Australia and South America, the sight was unforgettable. The comet's dust tail, caught by solar wind, developed multiple bright rays that curved across the sky like a brilliant fan. In recent years, several comets have captured attention, though none have quite matched the drama of Hale-Bopp. Comet Lovejoy C2011 W3 was discovered by Australian amateur Terry Lovejoy in November 2011. This comet proved to be a sungrazer, passing within about 0.2 solar radii of the Sun's surface on December 16, 2011. Most astronomers expected it to be destroyed by the intense heat and tidal forces. But remarkably, it survived, emerging from behind the Sun with a long, bright tail visible in the pre-dawn sky for weeks. Comet Eisen, c. 2012 S1, was discovered in 2012 and generated tremendous excitement. Predictions suggested it might become spectacularly bright, possibly even visible in daylight. But as Eisen approached the Sun in late 2013, it began to fragment. On November 28th, it grazed the Sun at a distance of less than 2 million kilometers from the solar surface. The comet did not survive. What remained after perihelion was a dispersing cloud of dust, and Ison quickly faded from view. It was a reminder that comets are fragile objects, and predicting their behavior is fraught with uncertainty. More recently, Comet Neowise C2020 F3 appeared in the summer of 2020, providing a welcome distraction during the early months of the COVID-19 pandemic. Though not as bright as Hale-Bopp, Neowise was easily visible to the naked eye from dark locations and produced stunning photographs, with its distinctive tail curving across the twilight sky. Millions of people worldwide took the opportunity to venture out and observe, many using the comet as an excuse to escape lockdowns and experience the night sky. The history of great comets reminds us that these objects, though predictable in their orbital mechanics, still retain an element of surprise and wonder. We can calculate their paths through space with great precision, but we cannot always predict how bright they will become or whether they will survive their close encounter with the Sun. Each new comet approaching the inner solar system carries with it the possibility of spectacle, the chance to inspire a new generation of observers, and the opportunity to remind us of our place in a dynamic, ever-changing solar system where the unexpected can arrive from the darkness with little warning, light up our skies, and then vanish back into the depths from which it came. Spacecraft missions to comets. For most of history, our knowledge of comets came entirely from telescopic observations conducted from Earth. Astronomers could see the coma and tails, track the comet's motion across the sky, and use spectroscopy to analyze the composition of the gas surrounding the nucleus. But the nucleus itself, the solid core that drives all cometary phenomena, remained hidden within the bright glow of the coma. To truly understand comets, we needed to send spacecraft to visit them up close. The first opportunity came with the 1986 apparition of Halley's Comet. Several nations, recognizing the scientific value and public interest, launched what became known as the Halley Armada, an international fleet of spacecraft destined to study the famous comet. Japan contributed 2 spacecraft, Suisei and Sakigake, which performed distant flybys, studying the comet's hydrogen coma and its interaction with the solar wind. The Soviet Union launched two ambitious missions, Vega 1 and Vega 2. These spacecraft had already successfully deployed landers and balloons at Venus, hence the name Vega, contraction of Venera Galli. After leaving Venus, both spacecraft continued on to encounter Halley's Comet, passing within about 8,000 and 3,000 kilometers of the nucleus respectively, returning images and valuable data. But the star of the Halley Armada was undoubtedly Giotto, launched by the European Space Agency, named after the Italian painter who had depicted Halley's Comet in his 1301 fresco, Adoration of the Magi. Giotto was designed for a close encounter, and it delivered spectacularly. On March 13, 1986, Giotto plunged through Halley's coma at a relative velocity of 68 kilometers per second, passing just 600 kilometers from the nucleus. In the moments before closest approach, Giotto's camera transmitted the first close-up images of a cometary nucleus, revealing an irregularly shaped potato-like object measuring 15 by 8 kilometers. The nucleus was dark, one of the darkest objects in the solar system, reflecting only about 4% of the sunlight hitting it. This darkness came from a crust of organic material coating the surface, material that had been processed by billions of years of radiation. Most remarkable were the jets. Bright plumes of gas and dust erupted from specific active regions on the sunlit side of the nucleus, creating features that looked like searchlights in the darkness. Giotto's instruments measured the composition of these jets, detecting water, carbon monoxide, carbon dioxide, and various organic compounds. The spacecraft also measured the dust particles streaming away from the nucleus, analyzing their composition and size distribution. At closest approach, traveling at enormous velocity through a cloud of dust particles, Giotto was battered by impacts. A dust grain weighing just a few tenths of a gram but moving at relative velocity of 68 kilometers per second hit the spacecraft with the force of a hand grenade. The impact knocked Giotto's camera out of alignment, ending the imaging sequence, but the spacecraft survived. Most of its instruments continued to function, and it transmitted valuable data as it exited the coma. Giotto's encounter with Halley was so successful that the spacecraft was later retargeted for a flyby of Comet Grigg-Skellerup in 1992. After the success of the Halley missions, scientists began planning more ambitious comet encounters. NASA launched the Stardust mission in 1999 with a unique objective: not just to study a comet, but to collect samples of cometary material and return them to Earth. Stardust's target was Comet Wild 2, pronounced Wild 2, a Jupiter family comet with an orbital period of about 6 years. On January 2, 2004, Stardust flew through Wild 2's coma at a distance of about 240 kilometers from the nucleus, capturing the first high-resolution images of a Jupiter family comet. Wild 2's nucleus was about 5 kilometers in diameter, heavily cratered and pitted, with jets of gas and dust erupting from various locations. During the flyby, Stardust deployed a collector filled with aerogel, an ultralight, porous material that could capture fast-moving dust particles without destroying them. The spacecraft emerged from the coma with thousands of cometary dust grains embedded in the aerogel. In 2006, after traveling nearly 5 billion kilometers, Stardust's sample return capsule re-entered Earth's atmosphere and parachuted to a landing in the Utah desert. Analysis of the returned samples revealed surprises. The dust contained expected materials like silicates and organic compounds, but also unexpected minerals like olivine and pyroxene that typically form at high temperatures. Some grains appeared to have formed in the hot inner solar system and were later transported outward, incorporated into the comet forming in the cold outer regions. This suggested that material was mixed throughout the early solar nebula on a large scale, challenging simple models of solar system formation. In 2005, NASA's Deep Impact mission took a more dramatic approach. Instead of simply flying past a comet and collecting samples, Deep Impact was designed to create an impact on a comet's surface, excavating fresh material from beneath the protective crust and analyzing it. The target was Comet Tempel 1, another Jupiter family comet. On July 4, 2005, Deep Impact released a copper impactor weighing 370 kilograms. The impactor was on a collision course with the comet's nucleus, while the main spacecraft, with its cameras and spectrometers, watched from a safe distance. The impact occurred at over 10 kilometers per second, releasing energy equivalent to about 5 tons of TNT. A brilliant flash of light erupted from the impact site, and a plume of ejected material streamed into space. The collision excavated material from beneath the surface crust, revealing pristine ice and dust that hadn't been exposed to space weathering. Deep Impact's instruments analyzed this material, detecting water ice, carbon dioxide, silicates, carbonates, metal sulfides, and complex organic molecules including polycyclic aromatic hydrocarbons. The mission was spectacularly successful, providing detailed information about the interior composition and structure of a cometary nucleus. But perhaps the most ambitious and scientifically rewarding comet mission to date was Rosetta, launched by the European Space Agency in 2004. Unlike previous missions that performed brief flybys, Rosetta was designed to orbit a comet for an extended period, watching it transform as it approached the Sun. Rosetta's journey to its target, Comet 67P Churyumov-Gerasimenko, took 10 years and covered over 6.5 billion kilometers. The spacecraft performed multiple gravity assist maneuvers at Earth and Mars to build up the velocity needed to match the comet's orbit. Along the way, Rosetta flew past 2 asteroids, Steins and Lutetia, providing valuable bonus science. In August 2014, Rosetta finally arrived at 67P, becoming the first spacecraft to orbit a comet. What it revealed was extraordinary. The comet's nucleus was a contact binary, 2 lobes connected by a narrow neck, giving it a shape reminiscent of a rubber duck. The nucleus was about 4 kilometers long, and like Halley and Wild 2, it was covered with a dark crust. But Rosetta's extended observations revealed the comet's surface in unprecedented detail. The landscape was alien and beautiful. There were smooth plains, boulder fields, cliffs hundreds of meters high, pits that might have been caused by subsurface ice suddenly collapsing, and layered terrain suggesting the comet had a complex formation history. Different regions had distinct characteristics, some smooth and dust-covered, others rough and icy. Active regions displayed jets erupting from the surface, carrying gas and dust into space. Rosetta watched as the comet's activity increased during its approach to the Sun, seeing new jets turn on, existing jets intensify, and the coma grow and brighten. In November 2014, Rosetta deployed a lander named Philae, which became the first spacecraft to soft land on a comet. The landing didn't go exactly as planned. Philae's harpoons, designed to anchor it to the surface in the comet's extremely weak gravity, failed to fire. As a result, Philae bounced, touching down 2 more times before coming to rest in the shadow of a cliff, where sunlight couldn't reach its solar panels. Despite the difficult landing, Philae operated for about 60 hours on the battery power, conducting experiments and transmitting data before shutting down. It detected organic molecules on the comet's surface, measured the temperature and density of surface material, and even attempted to drill into the surface, though the drill didn't penetrate as deep as hoped. After months in hibernation, Philae briefly woke up again in June and July 2010 when changing illumination angles allowed sunlight to reach its panels, transmitting a few more data packets before falling silent permanently. Rosetta continued its mission, orbiting 67P through its perihelion passage in August 2015, watching the comet's activity peak as it came within about 1 astronomical unit of the Sun. The spacecraft observed dramatic changes. Jets intensified, outbursts ejected large amounts of material, and the coma grew to enormous size. Rosetta's instruments detected water, carbon dioxide, carbon monoxide, methane, ammonia, molecular nitrogen, and dozens of other molecules streaming away from the nucleus. The spacecraft even detected complex organic molecules, including glycine, an amino acid, and phosphorus, a key element for life, providing further evidence that comets could have delivered some of the building blocks of life to Earth. On September 30th, 2016, as the comet headed back out toward the outer solar system, and Rosetta's solar panels struggled to generate power at increasing distance from the Sun, the mission ended in a controlled impact. Rosetta was commanded to descend slowly toward the comet's surface, taking images and measurements until the very last moment. The spacecraft touched down in a region called Oort, and its transmissions ceased. Rosetta now rests on the comet it studied for 2 years, a permanent monument to one of the most successful space missions ever conducted. These missions, from Giotto's daring plunge through Halley's coma to Rosetta's 2-year orbital campaign at 67P, have revolutionized our understanding of comets. We've seen their surfaces, analyzed their composition, watched their activity unfold, and even brought samples back to Earth. But even with all we've learned, comets continue to surprise us. Each new mission reveals unexpected details, challenging our models and raising new questions. Future missions are planned to visit other comets, perhaps to return larger samples, or even to demonstrate technologies that might allow us to deflect a comet if one were ever found to be on a collision course with Earth. The exploration of comets, these ancient wanderers from the outer darkness, is far from over. Comet composition and what it tells us. When astronomers describe comets as dirty snowballs, they're being both accurate and overly simplistic. Yes, Comets are primarily ice mixed with dust, but the details of that composition reveal a story stretching back to the very beginning of the solar system, offering clues about the conditions, chemistry, and processes at work when our cosmic neighborhood was forming over 4.5 billion years ago. The most abundant volatile in most comets is water ice, H2O, in its solid form. Depending on the specific comet, water ice can comprise anywhere from 50 to 80% of the nucleus's mass. This ice isn't the clear, crystalline ice we're familiar with from our freezers. It's more likely amorphous ice, a disordered form that results from very rapid freezing at extremely low temperatures, the kind of conditions present in the outer solar nebula. Mixed with water ice are other frozen volatile compounds. Carbon dioxide ice is common, as is carbon monoxide. Methane and ammonia are also present, though in smaller amounts. These ices have different sublimation temperatures. Carbon dioxide, for instance, begins to sublimate at lower temperatures than water, which is why comets often show activity even when they're quite far from the sun, before water ice starts sublimating significantly. The dust component of comets is equally important. Embedded throughout the icy matrix are silicate grains, compounds similar to the sand found on Earth. These include minerals like olivine and pyroxene, magnesium, and iron silicates that are common in rocky bodies throughout the solar system. There are also carbonates, compounds containing carbon and oxygen bonded together. Some dust grains contain metal sulfides, including pyrite or fool's gold. Interestingly, some of these minerals form at high temperatures, requiring hundreds or even thousands of degrees to crystallize. This presents a puzzle. How did high-temperature minerals end up in comets that formed in the frigid outer solar system? The answer appears to be large-scale mixing in the early solar nebula. Material that condensed near the young sun was somehow transported outward, perhaps by turbulence in the nebular disk, or by the dynamics of the forming giant planets. This mixing distributed inner solar system material throughout the disk, allowing it to be incorporated into comets forming in the cold outer regions. This discovery has forced astronomers to revise their models of solar system formation, recognizing that the process was more dynamic and complex than simple models suggested. Perhaps most intriguing are the organic compounds found in comets. Organic in this context doesn't mean biological. It simply means carbon-based. But these organic compounds are remarkably complex and diverse. Spectroscopic observations and spacecraft measurements have detected dozens of different organic molecules in cometary comae and in returned samples. Among the simplest are formaldehyde and methanol. Moving up in complexity, we find polycyclic aromatic hydrocarbons, or PAHs, ring-shaped carbon molecules that on Earth are found in coal, petroleum, and soot. Comets also contain more complex molecules, alcohols, ethers, aldehydes, ketones, and even amino acids, the building blocks of proteins. The Stardust mission, which returned samples from Comet Wild 2, detected the amino acid glycine in the cometary dust. The Rosetta mission found glycine in 67P's coma, along with phosphorus, a key element in DNA and cell membranes. These detections are profound. They demonstrate that the chemical building blocks of life, the ingredients necessary for biology as we know it, form naturally in cometary ices through non-biological processes. This has implications for the origin of life on Earth. During Earth's formation and early history, the planet was bombarded by comets and asteroids. Some of these impactors were comets from the outer solar system, rich in water and organic compounds. It's possible, perhaps even likely, that much of Earth's water was delivered by comets during this bombardment. The organic compounds needed to jumpstart life might have come from comets as well. In this view, comets aren't just fascinating objects to study, they're potential ancestors, cosmic seed packets that delivered the ingredients for oceans, atmosphere, and life to a young, molten Earth. The isotopic composition of cometary material provides additional clues about origins. Isotopes are versions of elements with different numbers of neutrons in their nuclei. The ratio of different isotopes can tell us about the conditions under which material formed. For instance, the ratio of deuterium, heavy hydrogen, to normal hydrogen in water varies depending on temperature and other formation conditions. Measurements of deuterium in several comets have shown that their DH ratio is generally higher than that of Earth's ocean water, though with significant variation from comet to comet. Some comets match Earth's ratio fairly well, while others are distinctly different. This suggests that Earth's water probably came from multiple sources, not just comets, but also water-rich asteroids from the inner solar system. The story is complex, still being unraveled by ongoing research. Comets also contain surprisingly high amounts of noble gases, elements like argon, neon, and xenon trapped within the ice. These gases are interesting because they're chemically inert and don't react with other elements, so their presence and abundance provide information about the temperature and density of the solar nebula when the comet formed. The minerals and ices in comets are often mixed at the molecular level. Not just ice chunks with dust embedded in them, but ice and dust intimately mixed together. When cometary ice sublimates, the dust that was locked within is released. This is the source of the dust in cometary comae and dust tails, and ultimately the source of zodiacal light, a faint glow visible in the night sky caused by sunlight reflecting off dust particles distributed throughout the inner solar system, much of it originating from comets. Studies of cometary composition have also revealed that different comets can have quite different chemical makeups. Comets from the Oort cloud sometimes show different ratios of volatiles compared to Jupiter family comets from the Kuiper belt. This might reflect different formation locations or formation times in the early solar nebula. Some regions of the forming solar system might have been richer in certain molecules than others, and those differences are preserved in the comets we see today. One particularly interesting finding is that comets contain clues about presolar material, grains that formed around other stars before our Sun even existed. These presolar grains, identified by their unusual isotopic compositions, formed in the atmospheres of dying stars or in supernova explosions, were ejected into interstellar space and eventually became part of the molecular cloud that collapsed to form our solar system. A tiny fraction of the dust in comets consists of these ancient grains, stardust in the most literal sense, carrying within them the nuclear signatures of stars that died billions of years ago. The composition of comets, then, is not just an inventory of chemicals. It's an archive, a library containing information about the solar nebula's temperature, density, chemistry, and dynamics. It's a record of where and when different materials formed, how they were transported and mixed, and what conditions were like in the outer solar system when comets first coalesced from the surrounding cloud. Every measurement of cometary composition, every new molecule detected, every isotope ratio determined, adds another piece to the puzzle of our origins, helping us understand not just what comets are, but what they can tell us about the beginning of everything in our corner of the cosmos. The life cycle of a comet. Comets are not eternal. Like all objects in the universe, they have lifespans, periods of activity, and eventual fates. The life cycle of a comet is a story of gradual transformation, from pristine icy bodies in the outer solar system to depleted, inactive remnants that may eventually become indistinguishable from asteroids. A comet's life begins in the cold outer reaches where it formed, in the Kuiper belt or Oort cloud. Here, at temperatures just a few dozen degrees above absolute zero, the comet remains frozen and dormant, potentially for billions of years. In this frozen state, a comet undergoes very little change. Cosmic rays and solar radiation slowly process the surface materials, breaking apart molecules and creating new compounds through radiolysis. But these effects penetrate only micrometers, or at most millimeters, into the surface. The interior remains pristine, unaltered since the comet's formation. The comet's active life begins when gravitational perturbations send it falling toward the inner solar system. The first pass is often the most dramatic. The comet enters the realm of the sun's warming radiation with a full complement of volatile ices. When it crosses the distance where these ices begin to sublimate, activity begins. For a long-period comet making its first passage, this can result in an impressive display. The comet may become very bright, developing extensive coma and long tails as fresh, unprocessed ice sublimates freely. But each passage takes a toll. Every time a comet swings close to the sun, it loses material. The exact amount depends on how close it gets, how long it spends near the sun, and how much volatile ice remains. But estimates suggest that a typical comet might lose several meters of material from its surface during each perihelion passage. This lost material, sublimated into gas and blown away by the solar wind, or ejected as dust particles, is gone forever, dispersed into the interstellar medium. For short-period comets that orbit the sun every few years or decades, this mass loss accumulates quickly over many orbits. With each pass, the comet has less ice to sublimate, and its activity decreases. The comet gradually fades. What was once a brilliant object becomes progressively dimmer. Eventually, after perhaps hundreds or thousands of orbits, depending on the comet's size and perihelion distance, the comet exhausts most of its volatile ices. As a comet ages, its surface changes. The dust and non-volatile material that was once embedded in the ice doesn't sublimate. Instead, It's left behind on the surface as the ice beneath it sublimates away. Over time, this creates a mantle, a crust of dust and refractory material coating the nucleus. This mantle acts as an insulating layer, inhibiting further sublimation of any ice remaining beneath. As the mantle grows thicker, the comet's activity decreases even if there's still ice in the interior. However, mantles aren't always uniform. Some areas of a comet's surface may develop thick mantles, while others remain bare or covered with only a thin dust layer. This creates localized active regions, areas where ice is still close to the surface and can sublimate when warmed by the sun. Jets of gas and dust erupting from these active regions become more prominent as the rest of the nucleus becomes quiescent. Eventually, even these active regions may become mantled and cease activity. What remains after a comet's volatile ices are exhausted is called a dead or extinct comet. This is an inert, rocky body, often quite dark, that follows a cometary orbit but no longer displays cometary activity. Extinct comets are difficult to identify because they look like asteroids. They don't have comae or tails. The only way to identify them is through their orbital characteristics, particularly if they follow highly elliptical orbits more typical of comets than asteroids. Astronomers have identified several objects that appear to be extinct or dormant comets. These objects, sometimes called rock comets or Manx comets, have cometary orbits but show no activity even when close to the Sun. Some asteroids in the asteroid belt, particularly among the darker types, may actually be extinct comets that have migrated inward over millions of years. The distinction between asteroids and comets, once thought to be clear-cut, has become blurred as we've discovered objects that share characteristics of both. Not all comets fade quietly into dormancy. Some meet more violent ends. Comets can fragment and break apart, and indeed, this happens fairly often. The forces that can destroy a comet include tidal stress from passing too close to the Sun or a planet, rotational disruption if the nucleus is spinning too fast, or structural weakness if the nucleus is loosely held together. When a comet fragments, it can create a family of smaller comets following similar orbits. The most famous example is the Kreutz family of sun grazers, named after German astronomer Heinrich Kreutz, who studied them in the 19th century. Hundreds of Kreutz sun grazers have been identified, most of them discovered by the SOHO spacecraft's coronagraph, which blocks the bright disk of the Sun to reveal faint objects nearby. These sun grazers are thought to be fragments of a much larger comet that broke apart centuries or millennia ago. Every year, several new Kreutz sun grazers are discovered as they make their fatal plunge toward the Sun. Most don't survive perihelion, vaporized by the intense heat or torn apart by tidal forces. Even without complete destruction, many comets show signs of fragmentation. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces after a close pass by Jupiter in 92. When it returned in 94, the fragments impacted Jupiter's atmosphere in a series of spectacular collisions observed by telescopes around the world and in space. Comet Schwarzmann-Wachmann 3 has been fragmenting gradually over decades, breaking into dozens of pieces that continue to orbit the Sun in a stream. Why do comets fragment? Part of the answer is structural. Comets are not solid monolithic objects. They're more like loosely consolidated piles of ice and rock, often described as having the consistency of a snowdrift or a gravel pile held together by ice. They have internal voids, weak layers, and regions of varying composition. When stresses occur, whether from tidal forces, outgassing creating thrust in asymmetric directions, or rapid rotation, these weak structures can fail, and the comet breaks apart. There's also evidence that some comets are contact binaries, two separate objects that gently collided and stuck together. Comet 7P Churyumov-Gerasimenko, visited by Rosetta, is an example. Its distinctive duck shape, with two lobes connected by a narrow neck, suggests it formed from two bodies that merged. Such structures might be more prone to breaking apart under stress. For long-period comets, even a single pass through the inner solar system can be their last. If a comet's perihelion brings it extremely close to the Sun, within a few solar radii of the surface, the intense heat can vaporize the entire nucleus. Sun grazers discovered by SOHO often simply disappear as they approach perihelion, boiled away completely by solar radiation. The ultimate fate of a comet depends on its orbit and how much mass it had to begin with. Short-period comets that survive many passages will eventually become extinct, their orbits gradually changing due to planetary perturbations until they're no longer recognizably cometary. Long-period comets, if they survive their passage through the inner solar system, will return to the outer darkness of the Oort cloud, where they'll remain frozen and inactive for thousands or millions of years until their next perihelion, if indeed there is one. Some comets receive gravitational kicks that eject them from the solar system entirely. A close encounter with Jupiter at the right geometry can accelerate a comet to escape velocity, sending it on a hyperbolic trajectory into interstellar space, a cosmic exile, wandering forever among the stars. Other comets might have their orbits altered so they collide with the Sun or a planet, ending their existence in a final blaze of heat and light. Scientists estimate that the typical short-period comet can survive perhaps 1,000 orbits before it loses so much mass that it becomes inactive. For a comet with a period of 6 years, like many Jupiter family comets, this means a lifespan of about 6,000 years from capture into short-period orbit to dormancy. Halley's Comet, with its 76-year period, has been in its current orbit for at least 16,000 years and has completed something like 200 orbits. If it can survive 1,000 orbits, it has perhaps 60,000 years left before it becomes dormant, though it might fragment or be ejected from the solar system before then. The life cycle of comets, from frozen beginnings through active middle age to dormant retirement or catastrophic destruction, plays out on timescales vast by human standards but fleeting on cosmic scales. These icy wanderers, born in the earliest days of the solar system, carry within themselves the seeds of their own transformation, slowly sublimating, fragmenting, and fading until they become unrecognizable echoes of what they once were, or vanish entirely, their atoms scattered across space, adding to the thin whisper of material drifting between the stars. Comets and Earth. The relationship between comets and Earth is ancient, profound, and ongoing. These icy visitors from the outer solar system have influenced our planet in ways both subtle and dramatic, from delivering water and organic compounds billions of years ago to creating spectacular meteor showers we still witness today. The story begins in Earth's infancy, during the period known as the Late Heavy Bombardment, roughly 4 billion years ago. During this time, the inner solar system experienced intense bombardment by asteroids and comets, leftovers from the planet formation process. Earth, along with the Moon, Mars, Venus, and Mercury, was battered by countless impacts. Among these impactors were comets, carrying with them water ice and organic compounds from the outer solar system. When these comets struck Earth, much of their material would have vaporized from the violence of the impact. But over millions of years and countless impacts, it's thought that a significant fraction of this material was retained, adding to Earth's inventory of water and organics. The question of where Earth's oceans came from is still debated. Earth formed in the hot inner solar system where water should have been scarce. Yet, our planet has vast oceans covering more than 70% of its surface. Did this water come from comets? From asteroids? From outgassing of minerals in Earth's interior? The answer appears to be all of the above, though the proportions are uncertain. Measurements of deuterium to hydrogen ratios in comets have shown that many comets have higher DH ratios than Earth's ocean water, suggesting they can't be the sole source of our water. However, some comets, particularly certain Jupiter family comets, have DH ratios closer to Earth's value. The current thinking is that Earth's water came from multiple sources, some from comets, more from water-rich asteroids that formed beyond the snow line but migrated inward, and perhaps some from minerals within Earth itself that released water when heated. Similarly, comets likely delivered organic compounds to the early Earth. The amino acids, PAHs, and other carbon-based molecules found in comets would have been added to Earth's surface during the bombardment period. Whether these cometary organics played a direct role in the origin of life is unknown, but they certainly enriched Earth's early environment with the chemical building blocks life requires. Today, comets continue to interact with Earth, though fortunately not through direct impacts. Instead, we experience cometary material through meteor showers, one of the most reliably spectacular celestial events visible from our planet. As comets orbit the Sun, they continuously shed material, dust particles released as the nucleus's ice sublimates. These particles, each typically the size of a grain of sand or smaller, are left behind in the comet's orbital path, forming streams of debris that spread along the orbit. When Earth's own orbit intersects one of these debris streams, we experience a meteor shower. The particles, traveling at tens of kilometers per second relative to Earth, slam into the upper atmosphere about 80 to 100 kilometers above the surface. The incredible velocity causes the air molecules in front of the particle to compress and heat, creating a brief streak of light as the particle vaporizes. This is a meteor, commonly called a shooting star, though it has nothing to do with stars. Different meteor showers occur at specific times each year when Earth passes through different cometary debris streams. The Perseids, one of the most popular and reliable showers, peak around August 12th and are caused by debris from Comet Swift-Tuttle, which orbits the Sun every 133 years. The Leonids, peaking around November 17th, come from Comet Tempel-Tuttle. The Geminids, actually associated with an asteroid-like object called Phaethon that may be an extinct comet, peak in mid-December and are among the best showers of the year. During a typical meteor shower, an observer in a dark location might see dozens of meteors per hour, all appearing to radiate from a specific point in the sky called the radiant. This radiant effect is a perspective illusion. The meteors are actually traveling on parallel paths through the atmosphere, but just as parallel railroad tracks appear to converge at a distant point, the parallel meteor paths appear to radiate from a point in the direction Earth is moving into the debris stream. Occasionally, when Earth passes through a particularly dense part of a comet's debris stream, we experience a meteor storm, with thousands of meteors visible per hour. These storms are rare and difficult to predict, but when they occur, they're spectacular. The Leonid meteor shower has produced several storms in recent decades, most notably in 1999 and 2001, when observers saw thousands of meteors streaking across the sky. Meteors larger than dust grain size, perhaps pebbles or small rocks, create brighter events called fireballs. Extremely bright fireballs, brighter than Venus, are called bolides. Very rarely, larger objects, the size of basketballs or boulders, can survive passage through the atmosphere and reach the ground as well. Meteorites, though most meteorites come from asteroids rather than comets. Cometary material is generally less dense and more fragile than asteroidal material, making it less likely to survive atmospheric entry. The threat of cometary impact, while real, is quite small in human timescales. Large comet impacts capable of causing global catastrophe occur on average perhaps once every tens of millions of years. Smaller impacts that could cause regional devastation occur more frequently, maybe once every few thousand years. The 1908 Tunguska event in Siberia, which flattened 2,000 square kilometers of forest, may have been caused by either a small asteroid or a cometary fragment exploding in the atmosphere. One of the most dramatic cometary impact events we've witnessed occurred not on Earth, but on Jupiter. In July 1994, the fragments of comet Shoemaker-Levy 9 collided with Jupiter in a series of spectacular impacts. The comet had been captured by Jupiter's gravity and torn into more than 20 pieces by tidal forces during a close pass in '92. When the fragments struck Jupiter's atmosphere 2 years later, they created enormous dark spots in Jupiter's clouds, some larger than Earth. The impacts released energy equivalent to millions of nuclear weapons, demonstrating the incredible destructive potential of cometary impacts. Witnessing Shoemaker-Levy 9's impacts on Jupiter made scientists realize that similar impacts could occur on Earth, though fortunately they're rare. Since then, astronomers have increased efforts to detect and track near-Earth objects, both asteroids and comets, that might pose impact threats. Several survey programs scan the sky nightly, discovering hundreds of new objects each year and calculating their orbits to determine if any might be on collision courses with Earth. If a threatening comet were discovered with sufficient warning time, perhaps decades in advance, we would have options for deflecting it. Unlike in Hollywood movies, nuclear explosions probably wouldn't be the best approach. Instead, more subtle methods like the kinetic impactor technique, where a spacecraft rams into the comet at high speed to slightly alter its velocity, or the gravity tractor method, where a spacecraft hovers near the comet and uses its own gravity to slowly tug the comet onto a different path, might be more effective and reliable. NASA's DART mission, which successfully impacted the small asteroid moon Dimorphos in 2022, demonstrated that kinetic impactor technology works, changing the orbital period of the target by over 30 minutes. While Dimorphos was an asteroid, not a comet, the principles would be similar, though comets' activity and their potential to outgas, creating unpredictable forces, might complicate deflection efforts. Beyond the practical concerns of impact threats and meteor showers, comets serve as a reminder of our cosmic context. We live on a planet that was partly built by material delivered from the outer solar system. The water in our oceans, the carbon in our bodies, perhaps even the organic molecules that sparked the origin of life, may have ridden to Earth on comets billions of years ago. Every time we see a comet gracing the night sky, or watch meteors streak overhead during a shower, we're witnessing a continuation of the process that helped create our world. A gentle reminder of our connection to the broader solar system and the cosmic processes that made Earth a habitable, life-bearing planet. Conclusion and reflection. We've traveled a long journey tonight, following comets from their frozen origins in the distant Kuiper belt and Oort cloud, through their spectacular transformations as they approach the sun, across their moments of glory in Earth's skies, and to their various fates as they age, fragment, or fade into dormancy. These icy wanderers, these ancient visitors from the solar system's earliest days, have shown us their secrets through centuries of observation and decades of spacecraft exploration. Comets are time capsules. They preserve in their frozen hearts a record of conditions in the solar nebula over 4.5 billion years ago. Every molecule in their ices, every dust grain in their crusts, tells part of the story of how our solar system formed, how materials were distributed and mixed, and what the chemical environment was like when planets were just beginning to coalesce from the surrounding cloud. We've learned that comets are diverse. No two are exactly alike. They vary in size from small ice balls just hundreds of meters across to giants with nuclei tens of kilometers in diameter. They vary in composition, some richer in water, others in carbon dioxide or carbon monoxide. They follow different orbits, some visiting the inner solar system every few years, others taking millions of years to complete a single circuit. They respond differently to the sun's heat, some erupting with jets and outbursts, others sublimating more gradually and steadily. The history of comet observation mirrors the history of human civilization. Ancient peoples saw comets as omens, signs from gods or harbingers of disaster. Medieval observers recorded their appearances alongside wars, plagues, and the deaths of kings. Renaissance astronomers began to measure their positions and understand that comets moved through space beyond the moon. Enlightenment scientists applied mathematics and physics, revealing that comets followed the predictable orbits governed by gravity. Modern astronomers have sent spacecraft to visit comets, landed on them, collected their dust, and analyzed their composition. Through all this, comets have remained objects of wonder. Even now, with all our scientific knowledge, a bright comet in the night sky still inspires awe. There's something fundamentally moving about seeing a comet, knowing that the light reaching your eyes comes from ice that formed before Earth existed, from dust that was part of the cloud from which the sun ignited, from organic molecules that perhaps contributed to the emergence of life on our planet. Comets remind us that the cosmos is not static. The solar system is a dynamic place, constantly changing, with objects moving, colliding, fragmenting, and evolving. Comets are part of this dance, falling in from the darkness, lighting up briefly, and then returning to the cold from which they came. They connect the present to the distant past and to the far future. They've been visiting Earth for billions of years, and they'll continue to visit for billions more, as long as the sun shines and there are icy bodies in the outer solar system to be perturbed inward. As we learn more about comets, we also learn more about the possibility of life elsewhere. If comets delivered water and organic compounds to Earth, they likely delivered similar materials to other rocky planets and moons throughout the solar system. Mars, Europa, Enceladus, Titan all received their share of cometary impacts during the solar system's early bombardment. The organic compounds we detect in comets are the same basic building blocks that life on Earth uses. Finding these compounds throughout the solar system, in comets, asteroids, and even in interstellar space, suggests that the chemistry of life may be common in the universe. Future missions will continue to explore comets. Scientists are planning sample return missions that would collect larger quantities of cometary material and bring it back to Earth for detailed analysis. There's discussion of missions that would land on comets and operate for extended periods, drilling beneath the surface mantle to reach pristine ice beneath. Some researchers have even proposed missions to visit the comets in the Oort cloud, though the enormous distance and travel time make such missions extremely challenging with current technology. Perhaps someday, human explorers will visit a comet, stepping onto its surface in the weak gravity, looking out at the stars from this tiny frozen world. They might extract water ice for drinking and oxygen production, mine organics for manufacturing materials, use the comet as a resupply station for missions heading deeper into the outer solar system. Comets, after all, contain valuable resources: water, metals, organic compounds. If humanity's future lies partly in expanding throughout the solar system, comets might serve as stepping stones, way stations in the darkness between worlds. But for now, comets remain what they've always been: visitors, messengers, wanderers from the deep. They ask nothing of us except perhaps to look up, to notice, to wonder. In our busy lives, consumed by immediate concerns, it's easy to forget the larger context, the fact that we live on a small planet orbiting an ordinary star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. Comets, when they appear, invite us to remember this context, to consider deep time, to think about origins and endings and the vast scales of space and time that govern the cosmos. When next a comet graces our skies, take a moment to go outside and look. Don't just glance. Stand there for a while. Let your eyes adjust to the darkness. Find the comet, that fuzzy patch of light with its tail stretching across the stars. Remember that you're looking at ice that formed in the outer solar nebula 4.5 billion years ago. That the organic compounds in that comet might be similar to the ones that helped start life on Earth. That the comet has been falling toward the sun for months or years or millennia, waiting for this brief moment when it passes close enough to warm, to sublimate, to shine. And remember that you're part of this story too. The atoms in your body were forged in stars. The water you drink may have come partly from comets. The carbon that forms the backbone of every molecule of life in your cells was cooked in stellar furnaces and scattered across space. You are, in a very real sense, made of star stuff, connected to comets, to planets, to stars, to everything in the cosmos. As you drift toward sleep, perhaps think about that connection. You're not separate from the universe, observing it from outside. You're part of it, woven into its fabric, composed of its materials, governed by its laws, participating in its ongoing story. And somewhere out there, in the darkness beyond Neptune, beyond the Kuiper belt, in the vast emptiness of the Oort cloud, countless comets wait, frozen and patient, for the gravitational nudge that will send them falling inward toward the sun, toward Earth, toward a moment when they might be seen and marveled at by curious beings on a small blue world who wonder about their place in the cosmos. Thank you for joining me on this journey through the realm of comets. If these calm, curious explorations help you unwind, or if they give you a peaceful way to end your day, I'd be grateful if you'd take a moment to like and subscribe. It helps others find their way here to this quiet corner of the cosmos, one sleepy soul at a time. Sleep well. Dream of ice and light, of wanderers from the deep darkness, of ancient messengers carrying stories from the dawn of time. Good night.